Welcome, everyone. Today, we're diving into the fascinating world of straintronics. Straintronics is the study of how mechanical strain, stretching, compressing, or twisting, can be used to control the electronic properties of two-dimensional nanomaterials like graphene, molybdenum disulfide, and black phosphorus. Unlike traditional electronics, which rely on electric fields or doping to manipulate electronic behavior, straintronics exploits the fact that these ultra-thin materials have highly tunable properties due to their atomic thickness and unique crystal structures. For example, stretching graphene creates pseudomagnetic fields that can localize electrons and alter their energy levels, enabling new quantum phenomena. Similarly, bending or compressing molybdenum disulfide can shift its band gap, allowing precise control over how it absorbs and emits light, making it ideal for flexible optoelectronics. Imagine a guitar string. Tightening or loosening it changes the pitch of the sound. Similarly, applying strain to a two-dimensional material tunes its electronic notes, unlocking new applications in quantum devices, energy-efficient transistors, and wearable technologies. Straintronics offers a path to ultra-low-power, adaptable electronic systems, making it a cornerstone of next-generation nanotechnology.
Straintronics is a field that harnesses mechanical strain to control and manipulate the electronic, optical, and magnetic properties of materials, particularly 2D nanomaterials. Unlike traditional electronics, which rely on doping or external electric fields to alter material properties, Straintronics leverages the inherent mechanical flexibility and atomic scale sensitivity of 2D materials like graphene, molybdenum disulfide, MoS₂, and black phosphorus. Strain-induced modifications occur because of changes in bond lengths, crystal symmetries, and electron band structures, enabling precise and reversible control over material behavior. Example: applying strain to graphene generates pseudomagnetic fields that can create localized quantum states, altering the material's electrical conductivity. Analogy: straintronics is like tuning a musical instrument. Stretching or compressing a string changes its pitch, just as strain modifies the notes of a material's electronic properties. 2D materials, consisting of a single layer of atoms, are uniquely suited for straintronics because of their exceptional mechanical flexibility and sensitivity to external perturbations. Their atomic thickness ensures that even small deformations significantly impact their electronic band structures and optical properties. Additionally, the absence of bulk material constraints allows 2D nanomaterials to sustain large strains, up to 10% or more, without breaking, far exceeding the limits of conventional bulk materials. Example: graphene can stretch by up to 20% without rupturing, enabling it to withstand extreme mechanical deformations while retaining its unique electronic properties. Analogy: 2D materials in straintronics are like ultra-thin rubber sheets that can be stretched, twisted, or bent to create entirely new patterns and designs. In graphene, applying strain alters the alignment of carbon atoms, creating pseudomagnetic fields that affect electron motion. These fields are not real magnetic fields, but arise from the distortion of graphene's honeycomb lattice, which changes how electrons interact with the material. The result is the emergence of Landau levels, discrete energy levels typically associated with electrons in a magnetic field, leading to novel quantum phenomena like localized states and valley polarization. Example: straining graphene nanobubbles has been shown to create pseudomagnetic fields strong enough to trap electrons in quantum dots. Analogy: straining graphene is like creating invisible barriers in a flat landscape, forcing particles to follow specific paths or become localized in certain regions. MoS₂ is a semiconductor with a tunable bandgap, making it ideal for optoelectronics. Strain modifies the bond angles and orbital overlaps between molybdenum and sulfur atoms, shifting the material's bandgap. Stretching the material can reduce its bandgap, enhancing its ability to absorb or emit light at specific wavelengths, while compressing it can increase the bandgap, reducing its conductivity. This strain-dependent behavior enables applications in flexible displays, photodetectors, and solar cells. Applying a 2% tensile strain to MoS₂ shifts its bandgap from direct to indirect, altering its photoluminescence properties. Analogy: straining MoS₂ is like adjusting the blinds in a window to control how much light passes through, allowing precise tuning of optical properties. Black phosphorus, a layered 2D material, exhibits anisotropic properties, meaning its electronic and optical behavior depends on the direction of strain. Applying strain alters the material's effective mass and carrier mobility, significantly enhancing or suppressing conductivity along specific axes. This directional tunability is critical for designing energy-efficient transistors and sensors. Example: applying a uniaxial strain to black phosphorus enhances its carrier mobility along one axis, enabling faster electron transport in that direction. Analogy: straining black phosphorus is like reshaping a racetrack, where the direction of the strain determines the fastest lanes for electrons to travel. Certain 2D materials, such as chromium triodide CrI₃, exhibit strain-tunable magnetic properties. Strain modifies the exchange interactions between magnetic ions, altering the material's magnetic ordering temperature and creating the possibility of strain-controlled magnetic switches. This behavior is particularly promising for developing spintronic devices, where electrons spin rather than charge carries information. Example: applying strain to CrI₃ has been shown to change its magnetic anisotropy, enabling control over its ferromagnetic behavior. Analogy: strain-tunable magnetism is like twisting a magnet to align its poles in different directions, allowing dynamic control over its field. Straintronics enables the design of flexible, stretchable, and wearable electronics by allowing materials to retain or even enhance their functionality under mechanical deformation. Strain-induced changes in conductivity, bandgap, or optical properties make 2D materials ideal for devices like bendable transistors, stretchable photodetectors, and conformable sensors. These applications are crucial for advancing technologies in healthcare, robotics, and consumer electronics. Example: flexible strain sensors made from graphene can detect subtle deformations, making them useful for real-time health monitoring or soft robotics. Analogy: flexible electronics powered by Straintronics are like wearable fabrics that adapt to your movements while maintaining their structural and functional integrity. Straintronics offers a pathway to create energy-efficient transistors by dynamically tuning the electronic properties of 2D materials. By applying strain, researchers can switch materials between conductive and insulating states, reducing energy consumption in digital logic circuits. Additionally, strain-induced quantum effects, such as pseudomagnetic fields or localized quantum dots, enable the development of advanced quantum devices for computing and communication. Example: strained graphene transistors operate at lower voltages, reducing power consumption compared to conventional silicon-based transistors. Analogy: strain-controlled transistors are like adjustable faucets that precisely regulate water flow, optimizing efficiency and reducing waste. The field of straintronics is rapidly expanding, with ongoing research exploring new 2D materials, advanced strain engineering techniques, and novel device architectures. Straintronics holds promise for applications in quantum computing, adaptive optics, and smart textiles. Emerging techniques, such as strain gradient engineering, aim to create complex strain profiles that enable multifunctional devices capable of simultaneous electronic, optical, and mechanical functions. Example: strain gradient patterns in MoS₂ have been used to create strain-tunable photonic circuits, paving the way for integrated opto-electronic systems. Analogy: the future of straintronics is like crafting origami from high-tech materials, where each fold introduces new functionality and versatility.